Hey everyone, welcome back. Today's explainer is a really fascinating one. We're going to unpack a critical, yet honestly often completely overlooked dimension of the renewable energy sector. We're looking closely at the SASB standards for wind technology and project developers, and we're specifically zooming in on the incredibly complex world of material sourcing. You know, for an industry that's literally defined by these massive, towering physical structures, its biggest vulnerabilities actually lie in the microscopic details.
It's kind of a crazy paradox when you think about it. We see these giant wind farms expanding across coastlines and plains, and they represent this bright future of clean energy. But underneath all that massive scale, what hidden risks actually power the wind industry? Well, the reality is that the entire sector relies on an incredibly fragile, largely invisible supply chain of highly constrained materials. Put simply, without them, the turbines just don't turn.
Okay, let's dive into this. Here is our roadmap for today. First, wind technology's hidden challenges. Second, the critical minerals bottleneck. Third, geopolitics and supply constraints. Fourth, mitigating material sourcing risks. And finally, tracking materials efficiency.
Let's jump right into part 1, wind technology's hidden challenges, the macro versus the micro. A single wind turbine is an absolute marvel of modern engineering, towering hundreds of feet into the air. But its ability to actually generate electricity efficiently, that depends entirely on tiny, specialized components tucked away inside the nacelle. That's the housing right at the top of the tower. It's like a giant puzzle where the smallest pieces are the most important. And this dependency is exactly why the IFRS Foundation and its SASB standards demand that companies disclose their supply chain vulnerabilities. These standards mandate that wind project developers and technology manufacturers report strictly on their supply chain fragility, because investors need to know exactly how exposed these companies are. I mean, a single missing component can literally halt a multi-million-dollar project in its tracks.
Moving right along to part 2, the critical minerals bottleneck, a microscopic dependency.
The clean energy industry, despite all of its incredible innovations, is fundamentally tethered to a highly restrictive supply chain. They rely heavily on raw materials that are frankly incredibly difficult to source. To really grasp this, we need to look at how the SASB standards define the problem. According to the text, a critical material is a material that is both essential in use and subject to the risk of supply restriction. So you're looking at this dangerous intersection of being absolutely necessary for the tech to work while simultaneously being at high risk of suddenly becoming totally unavailable.
So what exactly are we talking about here? Well, the SASB standards list some vivid, specific elements that create this massive bottleneck. We are talking about rare earth elements like neodymium and dysprosium. We're looking at critical minerals like tantalum and tungsten. And it also includes platinum group metals, think palladium and iridium, alongside stuff like antimony, cobalt, gallium, and graphite. Just looking at this list, you really start to grasp the sheer scale and complexity of the wind sector's dependencies. These are absolutely not materials you can just buy at a local hardware store, right? They require highly specialized extraction and refinement.
Which brings us perfectly to part 3, geopolitics and supply constraints, the global chessboard.
When your entire business model requires materials like neodymium, dysprosium, tantalum, and tungsten, you aren't just managing a standard supply chain anymore. You are actively navigating a global chessboard. The SASB framework outlines exactly why sourcing these specific deposits is such a high-stakes geopolitical thriller. It really comes down to 3 major constraints. First, a low substitution ratio. Basically, you can't just swap these materials out for something cheaper without completely wrecking performance. Second, the deposits for these minerals are heavily concentrated in just a few countries, which creates massive geopolitical bottlenecks. And third, there is fierce competition for these exact same materials from other booming tech industries. Combine all that, you get a highly volatile market that directly threatens the cost of local energy and really risks slowing down our broader global climate goals.
And this brilliantly illustrates one of the greatest ironies in modern wind technology. See, the industry has been actively upgrading from traditional drivetrains to what are called direct drive turbines. And why wouldn't they? Direct drives offer higher reliability and require way less maintenance. But here is the catch. To achieve that amazing reliability, direct drive turbines require significantly higher amounts of those critical constrained materials we just talked about. So by solving an operational problem on one hand, the industry essentially deepens its exposure to global supply chain shocks on the other.
All right, part 4, mitigating material sourcing risks, the SASB strategy.
So how do companies actually navigate this minefield?
Well, under the SASB metric RRWT440A.1, standard setters expect these companies to proactively manage and transparently report on how they're handling these exact vulnerabilities. The framework gives us 4 specific mitigation strategies companies are expected to employ to protect against input cost volatility and sudden supply shocks. Step 1. Diversify global suppliers, so you aren't reliant on a single vulnerable region. Step 2. Stockpile essential materials to weather short-term disruptions. Step 3 involves actually investing in research to develop alternative and substitute materials. And Step 4 is a big one, investing in recycling technology to try and reclaim these precious critical materials at the end of a turbine's lifespan.
Now, there is a super fascinating nuance in the reporting standards here. SASB absolutely requires companies to be specific about the risks they face and the strategies they use to fix them. But they explicitly state that companies do not have to disclose information that would compromise their competitive advantage. So, if revealing the exact name of a critical material they're struggling to source would cause competitive harm, the company can actually keep that specific material a secret. They just have to make sure they still disclose the nature of the risk itself and how they are managing it. It's this really delicate balancing act between transparency for investors and protecting corporate strategy.
And finally, Part 5, Tracking Materials Efficiency, Measuring the Impact.
Now, what's really interesting about this slide is the sheer scale we're dealing with. Because these critical materials are expensive, volatile, and so hard to get, wind tech companies have to obsess over physically optimizing their turbine designs. The mantra is basically, do more with less. We focused a lot on rare critical minerals, but metric RRWT-440B.1 also requires companies to disclose the massive volume of base materials they consume. Look at the top 5 by weight: steel, aluminum, fiberglass, carbon fiber, and copper. The metric tonnage of these materials required to build a modern wind farm is just staggering, and remember, their prices are also subject to global market volatility.
To figure out if a company is truly becoming more efficient, investors look at these 2 quantitative metrics. Sure, they track the total weight of those top 5 materials in metric tons, but more importantly, they zero in on metric RWT440B.2, the average top head mass per turbine capacity. To put that into perspective, they are measuring the mass of the nacelle and the rotor way up at the top of the tower and dividing it by the megawatt capacity of the turbine. Investors desperately want to see that ratio shrinking. They want proof that companies are reducing the physical weight at the top of the tower while maintaining, or even better, increasing the megawatt power output.
Actually achieving those strict efficiency goals takes a multi-pronged approach, which is detailed in metric RRWT440B.3. It's not just about using less physical material, though obviously that's a huge part of it. It's also about optimizing the capacity factor relative to the materials used and increasing the overall lifespan of the turbine. And crucially, this involves software. Companies are utilizing advanced operational control software, like SCADA systems, to dynamically maximize the output and efficiency of the turbine. They are essentially trying to squeeze every single drop of performance out of the physical materials invested in the structure.
So, what does this all mean for us? The crucial takeaway is this. The wind industry is an absolute masterclass in modern engineering, but it is currently tethered to a highly vulnerable, geologically constrained supply chain, which leaves us with a really big question to ponder. If the future of clean energy relies on the world's most constrained materials, how quickly can we innovate our way out of this bottleneck? Can we substitute, recycle, and optimize fast enough to meet global energy needs? It is a very delicate balance between rapid renewable expansion and the harsh realities of material sourcing. Thanks so much for joining me on this explainer, and keep learning.